Welcome to Astronomy Daily, your regular dose of the latest in space and astronomy news. I'm Anna.
And I'm Avery. We're thrilled to have you join us as we explore the cosmos and bring you the most fascinating discoveries from across the universe.
Today we've got a packed episode. We'll be diving into Jeff Bezos' bold vision for orbital data centers, the surprising rarity of technological civilizations in our galaxy, a disturbing trend of the northern hemisphere darkening, and a rogue planet that's defying expectations by growing at an astonishing rate.
Let's start with a big idea from a big name. Jeff Bezos, the founder of Amazon and Blue Origin, recently made a prediction that within the next 10 to 20 years, we could see extremely large-scale data centers being built in Earth's orbit.
That sounds like something straight out of science fiction, Avery. What's the driving force behind this concept?
Well, it addresses some critical challenges faced by Earth-based data centers, primarily power supply and cooling. Bezos highlights that space offers continuous access to solar power, uninterrupted by atmosphere or weather. Imagine 24/7 solar energy collection without clouds, rain, or night cycles.
And cooling, I imagine, is a huge factor for these massive computing facilities.
Absolutely. Temperatures in space can drop to negative 270 degrees Celsius in shadow. This extreme cold could significantly simplify cooling systems, making orbital clusters ideal for intensive computational tasks like AI model training, which demand constant, massive power input and generate immense heat.
It's an intriguing vision, but the technical and economic hurdles must be astronomical. We're talking about generating gigawatts of power and housing thousands of tons of equipment.
You're not wrong, Anna. To generate just 1 gigawatt of continuous electrical power in Earth orbit would require a solar panel array roughly 1.5 to 1.8 kilometers per side. That's an area equivalent to several major airports.
And the weight of those solar panels alone? Between 9,000 and 11,250 metric tons. Lifting that into low Earth orbit with current technology, even with the most advanced rockets like SpaceX's Falcon Heavy, would cost anywhere from $13 to over $25 billion and require hundreds of launches.
Then there's the heat. Nearly all input power becomes heat, which must be radiated into space. We're talking millions of square meters of radiators to handle a gigawatt of thermal load. Radiators tend to weigh more than solar panels, so add tens of billions more dollars to that price tag.
And that's before we even consider the actual AI server equipment, which itself weighs tens of thousands of metric tons and costs tens of billions. So while Bezos' vision is technically possible, the logistical, economic, and engineering challenges are truly enormous. It's a testament to the grand scale of what humanity might attempt in space.
From massive orbital infrastructure, let's turn our gaze to life beyond Earth. New research is shedding light on just how rare technological civilizations might be in our galaxy.
And the findings are quite sobering, Avery. According to research presented at the EPSC-DPS 2025 joint meeting, the nearest technological civilization in the Milky Way could be as far as 33,000 light-years away. For such a species to exist at the same time as us, their civilization would need to have survived for at least 280,000 years, and potentially millions.
These findings really underscore how specific the conditions for life, especially intelligent life, truly are. It's not just about a planet being in the habitable zone. It's about a delicate balance of geological and atmospheric factors.
Indeed. Dr. Manuel Scherf and Professor Helmut Lammer highlight the necessity of active plate tectonics, which is crucial for regulating carbon dioxide in the atmosphere through the carbon silicate cycle. This balance prevents either a runaway greenhouse effect or the atmosphere escaping into space, both of which would render a planet uninhabitable.
But even with plate tectonics, the clock is ticking. Carbon dioxide is gradually locked away in rocks rather than recycled. On Earth, photosynthesis is expected to stop working in about 200 million to a billion years due to declining CO2 levels. Planets need just the right amount to sustain a biosphere for billions of years.
Then there's oxygen. Not only is it needed for complex animals, but studies show that if oxygen levels fall below 18%, open-air combustion becomes impossible. Without fire, the smelting of metal is unfeasible, making a technological civilization, as we understand it, impossible.
So combining all these factors, the planet's ability to maintain a biosphere, the time it takes for technological life to evolve, which on Earth was 4.5 billion years, and the lifetime of a technological species, Dr. Scherf and Professor Lammer conclude that technological species are incredibly rare.
Their estimate of 33,000 light years to the next closest technological civilization puts it potentially on the other side of the Milky Way from us. It's a stark reminder of how unique our existence might be.
Despite these discouraging numbers, Dr. Scherf strongly advocates for continuing the search for extraterrestrial intelligence, or SETI. He says finding nothing makes their theory more likely, but finding something would be one of the biggest scientific breakthroughs ever. It's a quest for understanding our place in the universe, regardless of the odds.
Next, we shift our focus closer to home, to a fascinating and somewhat concerning study about our own planet. For nearly 2 decades, satellites have been quietly measuring the flow of sunlight and heat through Earth's atmosphere, and the results indicate a disturbing trend.
That's right, Anna. Scientists are reporting that the northern hemisphere is steadily getting darker compared to the southern hemisphere. This isn't about literal darkness, but rather its reduced ability to reflect sunlight back into space. This discrepancy could profoundly redefine global wind patterns, ocean currents, and even temperatures.
The study uses 24 years of data from NASA's CERES system, which tracks absorbed solar radiation and outgoing long-wave radiation. They found that the northern hemisphere absorbed about 0.34 watts per square meter, more solar energy every decade than the southern hemisphere. While it sounds small, it's statistically significant enough to upset Earth's delicate energy balance.
Several intertwined factors are driving this darkening. A major one is the loss of reflective surfaces. Melted sea ice and decreasing snow cover in the Arctic expose darker land and ocean, which absorb more heat.
Another significant factor is the decline in airborne particles known as aerosols. Tighter air pollution regulations, while beneficial for human health, have purged these small pollutants. Aerosols previously scattered sunlight and contributed to reflective clouds, bouncing radiation away from Earth.
Interestingly, in the southern hemisphere, natural events like Australia's massive bushfires and the Hunga Tonga volcanic eruption temporarily raised aerosol levels, enhancing sunlight reflection. But these spikes weren't enough to counteract the global imbalance.
This suggests a broken symmetry in Earth's climate system. For years, researchers assumed the planet would self-regulate, with clouds or ocean currents redistributing excess energy. But the data indicate clouds aren't fully compensating for these hemispheric imbalances.
This matters because the energy imbalance directly drives air and ocean circulation, the forces behind weather and climate stability. As the North absorbs more energy, heat transport patterns can be altered, potentially intensifying warming on northern continents.
The implications are broad. More severe summers in Europe and North America, interference with wind patterns, and increased Arctic ice melt. While these changes are slow, they accumulate, reinforcing climate change feedback loops. This also means global warming won't occur uniformly. Regions like North America, Europe, and Asia might see greater temperature rises.
For policymakers, it highlights a complex trade-off. Cutting aerosol pollution cleans the air, but also affects how the planet reflects the sun. Climate models need to capture this interplay more accurately. It's a stark reminder that small changes can subtly, yet profoundly, shift our planet's delicate energy balance.
Finally, we journey to the cold, dark depths of interstellar space, where a rogue planet is making headlines for its astonishing growth.
That's right, Anna. Recent observations from the European Southern Observatory's Very Large Telescope have captured a free-floating object known as CHA 11077626, pulling in gas and dust from its surroundings at a staggering 6 billion tons per second. That's a pace never before seen in a planetary body.
6 billion tons per second? That's mind-boggling, especially for an object that lacks a host star and drifts freely through space. It's behaving more like a young star, with sudden outbursts of brightness and magnetic accretion events, The lead author, Victor Almendros-Abad, even stated it blurs the very definition of what a planet is.
Discovered in 2008, Chow 110-77626 was initially thought to be a brown dwarf or a forming star. But at only 5 to 10 times the mass of Jupiter, it falls below the typical threshold for either. Stars need around 80 Jupiter masses to ignite fusion, and brown dwarfs require at least 13.
Yet despite its low mass, it's undergoing accretion, the very process by which stars are born. The dramatic brightening observed in 2025 mirrored exor bursts seen in nascent stars, linked to rapid accretion surges. They even found water vapor in its atmosphere during the burst, a chemical signature typically observed during stellar accretion, not planetary.
This discovery adds significant fuel to a long-standing debate about how free-floating planetary mass objects form. Are they failed stars, or are they ejected planets kicked out of developing systems? The data from Chat 11077626 leans towards the former, suggesting it formed in isolation like a star.
It's a testament to how much we're still learning about planet formation and the fluid boundaries of astronomical classifications. Future tools like the Extremely Large Telescope will undoubtedly help us spot more of these elusive rogue planets and understand their earliest evolutionary phases.
And that wraps up another exciting episode of Astronomy Daily. What a journey from futuristic orbital data centers to the profound rarity of alien civilizations, and from the darkening of our own planet to a planet behaving like a star.
It truly highlights the vastness and complexity of our universe and the incredible science being done every day. Thank you for joining us.
Be sure to subscribe wherever you get your podcasts so you don't miss our next episode. Until then, keep looking up. There's a lot to see in the night sky this week, what with supermoons and asteroid showers in particular.
Thanks, Avery. And I'm Anna, signing off until tomorrow, when we'll be back to bring you even more space and astronomy news. Until then, bye.